So, hello everybody. Can you hear me? Is this good? Okay. I was going to thank everybody for making it here, but then I look at the weather outside and then I think, where else would you rather be, right? So I'm Supreet. Other than taking pictures and creeping you out most of the time in the conference, I do research also in my free time. This is the work that I did with my previous advisor, David Irwin, at UMass Amherst. It's called Cloud Index Tracking. So let's get started. Okay, so this work concerns, is it working? Hold on, sorry. Okay, so this work concerns spot servers, which are gaining their prominence in the infrastructure as a cloud service offering. Okay, so let me put that in a context using a graph. There are going to be a lot of graphs. Sorry. So on the y-axis I have cost, and on the x-axis I have availability characteristics. Okay, so green is good, red is bad. So what I have here is compared to the on-demand offerings and the high availability reserved offerings, Spot sits right over here. Okay, so it's got the weakest availability guarantees on the cloud by far. So when you want a Spot server, you may not get it. Even when you get it, it may be taken away anytime. But in return for that, they're up to 10 times cheaper than the on-demand server. So what this has enabled is that there's a wide class of applications for which cloud was very expensive till now, but now they're able to access the cloud. Think of the discovery of Higgs boson. Think of the largest ever cluster created on the cloud. They all used Spot instances. Okay, so good as they are, they cause applications severe challenges. I think this mainly concerns with the way the pricing works. So in this graph again here, what I have on the y-axis is the price, instantaneous price of the server, and the x-axis I have the time. So as you can see, the Spot prices vary, and they vary big time. When the price goes above the user specified limit, the application experiences a server revocation. So both the variability and the revocations are not good. So price prediction has turned out to be an active area of research. And here is a brief sampling of the work. Most of the systems conferences have some sort of work related to this in the recent years. So as you can see, why this is important, right? So if you're able to predict the future price of a server, you can do several interesting things. One, you can compare and contrast different types of servers so that you can choose the one that best matches your application, not paying too much money. Second, you can put that red bar wherever, based on where you think is a good way to put it, so that your application experiences less revocations. And third, and probably most importantly, you regain your ability to come up with your budgets in a good way, right? It's not very variable as such. And that can be a deal breaker, as we've seen in John's talk yesterday. Okay, so while predicting the Spot prices is important, the ability to do it accurately is difficult. Okay? So to give an appreciation for why that's difficult, some numbers here. So Amazon sells about 68 different types of VM configurations. Okay? Each of those come under Linux or Windows OS, housed in any of the 2 to 5 data centers that they have in 14 regions around the world. And each combination of this is sold as a separate Spot server market. And that's kind of intuitive to see why that is the case, because let's say you have an idle server sitting in Frankfurt at 8 a.m. in the morning. You have to use that server at that location at that time, right? So it kind of makes sense. But what this tells us is that there are 7,600 Spot markets worldwide. Okay? So that's a big number. And that poses a lot of challenges to the current prediction models. So I'm going to highlight 3 of those significant challenges. First, because there are like so many markets with their local supply-demand dynamics, it's very unlikely that there is one grand single model that predicts the price of all these markets, right? So very unlikely. Second, even though we know how to use Spot servers, we do not know how Amazon sets the prices internally, right? And in fact, Amazon is known for changing these prices on a whimsical basis over the period of time. Third, basically concerns, if you think about other spot markets like electricity, right? So the price sort of correlates with external factors like weather. So if the weather is good, the price is going to be somewhere. So you can predict those things. When it comes to cloud compute, we don't know what affects cloud compute, right? So there is no visibility into external variables. Somebody suggested there is this Kim Kardashian flash sale factor that affects the way the services move up, but then we have filed it in the future works category. So given these challenges, the current models, what they're left with is they look at the past price trace and try to predict the future. Okay. So in this work, what we say is, this work started by us observing that similar problems exist elsewhere. Okay, and that is the financial markets. So if you look at the NASDAQ and the NYSE, there are about 6,000 stocks, independently varying stocks, right? So investors now have to make a choice as to where do I invest money, what do I buy, what do I sell. Okay, so what do the investors do? Our friend Jim Cramer, right? We all know him. So he makes bold predictions on individual stocks. Sometimes they work, sometimes they don't. Right? So this is similar to the current prediction models for individual spot prices. In fact, there's an efficient market hypothesis which states that you cannot consistently beat the market by making future predictions on prices. So if you can't beat the market, what do? The next best option is to match the market. That's where the idea of market indices come into picture. So think of S&P 500 and Dow Jones Industrial Average. So what they do is instead of looking at individual stocks, they combine a bunch of stocks and then make predictions on those. And when you combine a bunch of stocks, the variability reduces and they become more predictable. Right? So the key insight of this work is that similar thing holds good for the cloud spot markets as well. And we say that rather than focusing exclusively on predicting individual markets, we should look at the markets in aggregate. And by doing so, they become very stable and very easily predictable. Okay, so in the next 10 minutes or so, I'm going to split the talk into two broad parts where I'm going to introduce the notion of the cloud index. What's our intuition behind it? How do we construct an index? And I'm going to show some validation on the EC2 spot market. In the second part, we're going to use the index to come up with a design called index tracking that lets us achieve predictability. Okay. The first part. So what's the intuition? So why should an index work for the cloud spot markets, right? So I made two observations based on the underlying characteristics of the current clouds. The first concerns the dependence of VMs. So Amazon sells a bunch of VMs. Like think of M4 large, M4 extra large, M4 2x large, 4x large, stuff like that. So underneath, they're all multiplexed onto similar or same type of physical machines, right? And we don't know how Amazon or any of these cloud providers chop these things into VMs and how that changes over time. So in absence of that information, we make an argument that not all spot markets are free of mutual interference. So you cannot easily predict, or it's not prudent to predict at the individual level. The second insight is about the stability of the idle capacity. So this stems from the recent papers that Google and Microsoft have published. One was in SoC and one is in SOSP. So what they say is that when you look at the data center as a whole, the CPU utilization varies considerably, okay? But the total number of VM allocated to the users, that doesn't vary at all. The variation is about 2 to 6%. So if the VM allocations don't vary, the idle capacity conversely should not vary, right? So as anybody in like Econ 101 would know, if you have a constant supply and a constant demand, the prices should also be constant. So we say that if you look at the data center as a whole, you should have a stable prices. So that gets to our hypothesis that we say that based on these two, observe the spot markets in aggregate. Now we know the two aggregate levels that we want to look at. One is the server family level, and the second is the data center level. And we should expect to see stable prices. Okay, so let's construct an index and apply it to the spot markets. Okay, first thing, what's a market index, right? So S&P 500, right? We've all looked at that. So a market index is basically a characterization of a group of items. So you have a bunch of stocks, you want to put a number. So S&P 500 is like 2,500, things like that. So how does it work for the cloud server? So we have a bunch of cloud servers, we want to give a number to that. Okay, let's characterize each server. Very straightforward. A server has a price, it has resources. Price in the numerator, resources in the denominator. So once we characterize each server, we combine them using simple arithmetic average. Okay, so no rocket science here, very simple. So finally, what does this number tell us? A cloud index will represent the average price per unit of compute time amongst a selected group of servers. Okay. Okay, so let's take this notion and apply it to the market and see if our hypothesis is even true. So this is what we have seen. This is how the individual spot markets vary. Now let's say I consider all the markets in a data center and apply the index. So this is how it looks. Okay? So I want to make two broad comments. The axes are completely different. That's 1 to 128 and this is 0 to 2. But even then, you see that the spiky behavior is gone and it's very stable. So what this allows me is that, so if at this point of time, somewhere here, if I want to make a prediction on how the price is going to be 1 month later, you can make a prediction and then you can be pretty sure that it's going to be there, in that ballpark area. Okay. How about we look at the server family level? So I have shown two server families, the compute optimized and the memory optimized. Each of these have about 20 to 25 servers. So even at that level of aggregation, right, the spikes are gone. So they're all very stable and you can make easy predictions. Okay, so that kind of validates our hypothesis that you should look at the markets in aggregate and don't look at the markets individually. Okay, so with that in our kitty, what we can do is we want to design a server hosting mechanism that actually helps us with cost predictability. Okay, so I'm going to talk about two building blocks and then we'll get to the design, which will become intuitive then. Okay, the first concerns index tracking funds in financial markets. So simply put, these are investments that track an index. So what I have in the graph is the y-axis I have the returns and the x-axis is about 10 years. The red color line is the S&P 500, how that's moving, and the two orange and the blue are two index tracked funds from Vanguard. So as you can see, the lines are virtually indistinguishable, right? So the question is, how are they able to so closely track an index? And the answer is very simple. So S&P 500 has 500 stocks. So you create a portfolio such that you buy one of each stock and you will match the performance of S&P 500, right? So now you see where I'm going, right? So we have a cloud index which is reliable and stably predictable. Now we want to think of creating a cluster. So I want to create a cluster such that I will incur a fixed cost or a predictable cost. So what I'm going to do is I'm going to pick servers from my index and then create a cluster, right? And it's going to have a predictable expense, just like this. But there's a problem with that, right? So it's not scalable, it's not even simple, right? So we want to enable predictability at the level of individual server, not a cluster of servers. That's where the next concept comes into picture. So it's called the server hopping in cloud markets. This was based on the work published last year. So the idea is again very simple. So there are two spot markets here. There's a containerized application running in spot market A. At some point it realizes that market's not good. There's a better market. So it just transparently migrates itself to another market, continues to run. So there's a disruption period, of course. But now you get to execute on an efficient market. And if the application is not aware of it, it is transparent, right? So that's an idea. So combining these two, we come up with our design. It's called the index tracking by server hopping. Again, the goal is very simple, right? So we create an index and we want to achieve an index level efficiency by hopping despite the market volatility. Okay, first, it's in 3 steps. So you have your application, your workload, you know how it's going to look and you know what it needs. So determine a broad set of servers that can satisfy your need. Okay? So hopefully that's broad enough and that's wide enough that you get a stable index. Once you do that, you select a server, start running the application on that so that it's below the index level. Now as the market conditions might change and the server might become above, it might jump over the index level, then you got to make a transparent hop to another server that does. Okay? So as you can see, this is straightforward. The interesting bit in this is, how do you choose a server, right? Because you don't want to make too many hops. At the same time, you want to also achieve the efficiency. So we experimented and analyzed many different approaches. They're all in the paper. But the one that always wins, well, mostly wins, is what is based on, again, a construct derived from the financial world. Is called the Sharpe ratio. So on the numerator, I have Pi is the server, okay? So the server is gaining over, so you pick a server that's better than the index. So this numerator gives us how much better than the index level I am, and the denominator gives what's the probability of that varying. So you want to basically balance the risk and the reward. You want a server that is below the index level, but it doesn't vary too much. So once we do that, I think it's trivial after that. Okay, so we have a prototype that works on EC2 based on Linux containers. And I also have a bunch of cloud indices applied to worldwide markets. If you're interested, you could please click on that link and check it out. Okay, in terms of evaluation, I have two simple questions. One, we talked about index tracking. So does index tracking really achieve predictability as we were hoping? And second, how does it compare to other methods? So what are the other approaches? Okay, I make comparison with two other approaches. The first one is the static prediction or the spot leap. So I look at the markets. This is the Jim Cramer method. I look at the market, I pick the best server, I run on it until either the job is complete or I get revoked. Then I repeat the cycle. Second one is the hotspot. This is the 2017 work. Essentially, here is you're chasing the most cost-efficient server by making migrations. Third is the index tracking, where you define an index and you want to achieve that index level. So you hop only when you are not meeting the index level. Okay, so these are the three things. So we have many experiments in the paper, but I'm going to highlight just two of those. The first one is a long-running single-node application. They're contrasting in nature. That's why you have these two. So second one is the synchronous but parallel jobs. So we run these experiments for a period of 6 months on Amazon EC2. I'm not going to get into the details of the configuration of these experiments, but I want to highlight how the performances vary. So I have two graphs, one which measures the cost, second which measures the availability. So cost on the y-axis and three techniques on the x-axis. Okay? So index tracking sits in the middle. So on the dotted line indicates the index level. That's the target we were hoping to be under, and we are under that. And in terms of availability, this is how it looks. So as you can see, hotspot reduces the cost. The blue bar reduces the cost the most, but it pays a price in terms of not having good availability. It only has 1 9 of availability, whereas other methods have 2 9s of availability. How does it change when we look at the parallel jobs? So that job ran for 6 months. Now, these are short jobs, but they're coordinating multiple nodes. When that happens, hotspot price goes up, because when there are multiple nodes and each of the node is individually making its decision on how to migrate, how to optimize its cost, it affects everybody. So it not only is bad in terms of cost, but also in terms of availability. Okay, so two simple takeaways from this. Did we achieve the index level? And the answer is yes. And in terms of comparing the methods, we seem to get the best combination of cost and availability across the spectrum of approaches. Okay. So to conclude, I highlighted the problem of the cost uncertainty that exists in the spot markets. We propose a notion of cloud index and then design a technique called index tracking by server hopping. And our experiments and evaluations show that we are able to turn these variable priced spot markets into something that's more predictable. With that, I thank you for your patience.